So today we'll be continuing with our Coyotes and Wolves problems, except we will be taking the next step up to make it a little more complicated. Instead of a nice, well-defined count and problem with the Arizona Sonora Desert Museum, where we have a number of tall wolves, short coyotes, tall coyotes, already enumerated, so it's known, and we can just do the direct probability calculations. Now we'll be taking a step into, let's say, the desert or the wilderness somewhere in Arizona, where we know the probability of encountering a coyote and wolf are about equal, but we don't know much about the individual heights of the population of the coyote and wolves. And so we're just going to be representing the overall height function or height distribution over the entire population. And so we'll be stepping through how to do that and then how to actually solve the problem like before. So this is just the next step up from the coyotes and wolves problem. And so a key idea here that we're going to be talking about, and this is maybe one of the first key theorems that I'll mention in this class. So there's a central limit theorem, and this is in statistics and probability theory, to be specific, for those that are interested. But we had talked about last lecture and lecture before, in this entire semester, about independent variables, and we call them like random when they can take multiple values, and so we're independent random variables, and they're summed. So for example, if we know the percentage or the probability of a heads or tails in a coin flip, we know it's about 50-50. However, if we take 10 coin flips or 100 coin flips, if we take the sum of the outcomes, so when summed, tends towards a normal distribution. We haven't encountered this term before, so I'll go ahead and define it. This is like the bell curve almost, if you want to think about it visually. This is the bell curve distribution. Even if the original variables are not. What does this mean? So I will continue with the coin flip example. Let's say we are counting the number of heads in a coin flip, and so we're just tossing n equals 1, and we're going to do the probability. And so we're going to plot the probability on the y-axis and then the number of heads on the x-axis. And so we have 0 and 1, so we can get about a 50-50 equal chance of heads or tails with one coin flip. So that doesn't look, like a bell curve yet, but let's say that we had n equals 10. Again, we're going to do the number of heads. So this is 5, this is 0, this is 10. So there's some, we're going to plot the probability still. There's some, likelihood of, there being 0, 1, 2, 3, 4, or 5, sorry. Am I missing 0, 1, 2, 3, 4, let's split this, 5, 6, 7, 8, 9, and then 10. And so, it's starting to take a little bit of shape where, if we flip 10 coins, it's really unlikely that all 10 are going to be heads or 0 of them are going to be heads, but it's more likely that they're somewhere in the middle. However, if we take n equals to 100, this pattern really starts to show up. Instead of just drawing these boxes now, I can almost just draw like a little curve. Something like a bell curve. Where the number of heads is most likely to be 50. And we get less and less likely as we get more heads or less heads. And so it kind of takes this shape of a curve. And so this is actually very, very useful in representing populations, for example. So I've just been talking about heads and tails. And the overall idea of this heads and tails discussion is to show you that as the number of trials goes up, it tends towards this normal distribution, even though it's just 50-50 for the heads and tails. But this is actually very, very helpful for us, because if we're given something we don't know a lot about, but we know the distribution of how it's supposed to behave, we can make decisions based on the distribution without actually knowing the underlying counts or exact population statistics. And so I'm going to go ahead and throw an equation at you guys just to get you familiar with it, so you've seen it before. However, this is not something to commit to heart, but this is how the normal distribution is written out. And so basically, f of x, which is basically the p that we plotted, so p of x, where this is the y-axis, so x is the number of heads, is equal to this funky factor, which is something called sigma divided by square root of 2 pi e to the negative 1/2. Then we have the x from before, notation called mu. We've got the sigma again, and we square that. And this is equivalent to writing something like a special n for the normal distribution, and then it takes two parameters, mu, and then the sigma squared. And so this is a lot to digest just at first glance, but we'll go ahead and break it down. So this is just an equation to represent the plot that we see on the farthest right, number equals 100 trials. And this just tells the person doing the calculation what the probability is at any given x point. And we also have this mu and this sigma that we need to define, and we can see it over here too. Mu, which is this special looking u, it's called mu, is representative of the mean, the average outcome for your normal distribution. And so, for example, in n equals 100 trials, if you flip a coin 100 times, you would expect about 50 of them to be heads, 50 of them to be tails, because you had a half probability like before. The sigma, on the other hand, is a little bit tricky. And so the sigma is represented is the standard deviation. And this basically is a measure of spread from mu. And when we do the sigma squared, this is called the variance. And so for this normal distribution, the parameters that you need are the mu and the variance in order to plot the entire function. And then we can just easily get the probability of each individual outcome because it's dictated by this overall function. And so, like I said before, this is useful. The normal distribution is useful when the exact underlying outcomes are not known. And so let's look into the Coyotes and Wolf problems and see how we can start applying it. So let me first just show you how the sigma and the mu, or the variance and the mu, affect the overall look of the normal distribution. And so I showed you a plot with the 100 outcomes of the heads and tails. And now let's do something where I actually enumerate the normal distribution as we've seen before. So the mu is 2.0, and we're going to say the sigma squared is 0.2 squared. And so the standard deviation is 0.2. And so how does that look? We've got the mu, or like the x over here. Sorry, not the mu. We've got the x over here. We can draw the mu on the x. We've got this probability function. And 2.0, this is the mu. And so we know from how it looked like before that that is the peak of the bell curve. And if we care to enumerate how the plot looks, how big the spread is, and just in general the overall shape, there's two ways in which we can do it. We can either go into a graphing calculating function of which we can just plug in the actual equation that we've enumerated before, or we can actually just try individual values of x's that we care to enumerate the individual probabilities because we have a function. And so I'm just going to go ahead and approximate it, but it basically looks something like this, where with a 0.2 sigma, we basically get a spread that kind of looks like this, where you've got a peak over here at 2, and it kind of petters out and tails off. And so you can see that it's like 0.6 from each side of the mu. And so this is like for sigma squared equals 0.2 squared. However, if we draw this again with like a different distribution, let's just do 2.0, and then instead let's make the sigma bigger, like 0.4. What we would instead get is the same sort of peak at a mu equals to 2. However, these tails are going to be a little farther out. And so what this means is that the spread is bigger. And so you're getting higher probability to the values that are farther away from the mean. And so this is just to give you a representative example of like how the spread or the standard deviation and variance affect the normal distribution. But there's many different ways of which you can kind of plot these, and you'll have to do some of these in your homework. So now we've seen how like the variance affects the overall look of the plot. Let's go ahead and look how the mu changes the overall look of the plot. And so we're going to go ahead and revisit the Coyotes and Wolf problem. So Coyotes and Wolf revisited. Let's say the coyote population is equivalent to normally distributed around 1.8 meters tall, and it's got a variance is equal to 0.2 squared. And we'll say the wolf is a little taller, so it's like 2.1 meters, and the sigma squared is about the same. It is the same. So this is needed in order for the calculations to work out nicely. However, we could change the sigma, and you can analytically derive how that would affect your problem and how it would look in the overall plot, as we'll see in a second. And so we've changed the mu now, kept the sigma the same. Let's go ahead and plot it. So this is basically plotting the heights of the wolf and the coyote population with their respective probabilities. And so we can exactly look how likely a wolf of 0.3 meters is, or 0.2 meters, and that's how we're going to go ahead and solve the problem. And so we've got height, and then we've got the probability. And so I'm going to go ahead and maybe draw 1.8, 2.1, the original mu's. Let's come out 2.4. Let's go 1.5, and then dot 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 dot. It goes out. But I'm just going to draw the actual important region where the probabilities are a lot higher than negligible. And so, as before, I know that I've got a mu at the top of the bell curve. I know I've got a second mu on the other one where that represents the wolf. And so I can basically draw the bell curve as such for both of these, where one of them, let's say the coyote, and then we've got the wolf. And there's some sort of underlying overlap between the two plots. What we're going to see is that that's actually how we are going to make and define the probability of the error of this overall prediction, and also what's the quote unquote decision boundary, such that if we see a wolf that is 2 meters or 2.1 meters or 2.05 meters, what is the probability of it being a wolf versus a coyote, and how does that affect overall population probability if you change the mu and the sigma. And so we're just going to go ahead and analytically derive that and then use some code to plot it out. And so I'm just going to write this. If we see, same as before, if we see an animal that is 2 feet tall, is it more likely a coyote or a wolf? That's what we care to answer. And so just like before, we can go ahead and just start writing down some of the facts that we know about the problem. We know that, just like before, we want to find, let's just write some facts. We want to find the probability of a wolf given the height is equal to 2, right? And what is this in relation to the probability of coyote given the height is 2? And using the Bayes formula, using Bayes that we've derived before, we know that the probability, let's say, of a wolf given a height is equal to 2 is equal to the probability of the height. Height is equal to 2 given wolf times the probability of a wolf over the entire probability of the space of the height is equal to 2. Similarly, we have another formula for the coyote that looks exactly the same, except that we're going to be replacing it with the coyote. So equals 2. And then I'll just go ahead and finish this so that it's just complete. Coyote, probability, coyote over probability of height is equal to 2. And so we've already wrote out what we need. We care to get this, okay, this relation. We've got the exact formula. And so we can go ahead and just plug and chug. And so what we can ask, let's do ... What is, at what height is it more probable that an animal is a wolf? At what height is it more probable that an animal is a wolf? That is what we care to find. And so we're finding a specific height x in the distribution space that we had just plotted right here. We're finding some x here such that after this x, it's more likely to be a wolf than a coyote. And so we can, instead of using the exact counts, instead of using counts, probabilities, we can directly use the formula. Cool. So at this point, we're just doing the same calculations we had before, where we know all these values. By values, I mean, we know these guys, or we can at least analytically write them out. We just have to simplify. And so let's say, so we're doing at what height? So we're doing at what height? Height x is an animal more likely a wolf. And so we would 2 is probability of the wolf given height equals x is greater than probability of coyote given height equals x. Okay, we've got the equation. We can go ahead and do the math. 1 over 2 pi, and there's a sigma in here too. We've got e to the 1/2, negative 1/2 of the x that we care to find. We've got the mu of the wolf, and then we also have the same sigma from before, and that's squared. So that let's box this guy. What is this? This normal equation is defining this guy right here. The probability of a height equals 2 given a wolf, which is exactly what we plotted out right here. Probability over height. Similarly, we're going to have another normal equation that does the same thing for coyotes. And so we're just plugging and chugging with the formulas. There's nothing special that we're doing here. We're just taking the equation, using it instead of the actual probability, and you'll see how it'll fall out. So that's the first part in our base. The second one is the probability of wolf. So before, and this is an important assumption. Let's say for the first try, this does not have to necessarily go through or for every single time. Probability of wolf is equal to probability of coyote, which is equal to 0.5. What this means is that equal probability of seeing, but this does not necessarily have to happen. You'll see in the homework problem that I actually changed the probabilities. And so this is just for simplicity, but I'll go ahead and just write it out so that it can fall out. Probability of wolf, and that's over probability of height is equal to 2. And then again, doing the same thing, or 2 pi, we've got the sigma. We're going to do now for the coyote, 1/2 x. This is the second mu, same sigma. And then we've got probability of coyote over probability of height is equal to 2. Okay. Now, note from before, since we have the probabilities being equal, we can simplify and basically get rid of this, and then get rid of these two since they're the same. So we're basically just simplifying on both sides. And what we're left with is exactly the normal equations with the different mu's. Negative 1/2 x minus 1 sigma squared 2 pi sigma e negative 1/2 x u1 sigma squared. So we just simplify, and then we got this, and then we can do some more simplification. So what we want to do is we want to get rid of the front factor, which is the same on both sides. So that becomes 0. Okay, and so then we can have this guy is in what relation to this guy? This is what we care to simplify now. And so what we can do now is take the natural log, take ln, and I'm just gonna take the ln, which basically gets us 1/2 x mu1 squared, and then we've got negative 1/2 x mu1 sigma squared. This is the natural log, take the natural log, and then we're gonna flip the sign. Because we're dividing by a negative, and so this becomes x mu1, and then this sign had flipped because we have gotten rid of the negative up front. And then as you can see here, we can go ahead and do multiplication of two factors. So we can take this side and spread it out, and this side spread it out, so that we write out the whole equation. And as you can see, we could probably get rid of the sigma squared because that's a common denominator. And so we're going to go ahead and get rid of the sigma squared. And what this becomes, and after simplify, I know this is a lot of math, we're almost done. What this will come is we've got x squared minus 2x, we've got this mu1, and then, oops, sorry. No, mu0. And then what this becomes, let's go ahead and simplify. Go ahead and get rid of this guy. Go ahead and get rid of this guy. And then we can go ahead and move this. Simplifying from there. Then we can go ahead and divide it. So let me just demarcate the steps. This was a step, this was a step, this was a step, and then the final simplification. So x is greater than this value. It's more likely a wolf. So we've actually directly enumerated what that x value is. And so if we look at the plot that we did before, u1 plus u2 divided by 2, that's actually the middle of the intersection of the distribution, where this point is actually the x that we found. And this is the optimal decision boundary. Such that if we classify it as such, we will minimize the error. What is the error, you say? So with the mu1 and mu2, we can directly enumerate it, but we can see that the error is when both classes are incorrectly classified. And so if we're always saying that if you're over this x value, that you're going to be a wolf, or it's more likely to be a wolf, then we're going to get all of these guys over here wrong, where it's coyote that may be greater than this optimal decision boundary. Similarly, where we have short wolves, we're going to also accumulate some error. So the error is represented by the area under the curve. And so more formally, now that we found this x, the probability of error becomes the area under the curve. So this is, let's say, negative infinity. So this is an integral. We've already found the x. And so what I'm going to do is I'm going to try to find the probability of the wolves first being incorrectly identified. So this is the probability of a wolf, probability of the wolf error, where it's incorrectly classified from that decision boundary on the left. And this is just simply the probability of the height is equal to x, given that it's a wolf, plus that probability on the right side, which is the coyote x to infinity of the same thing. Probability of height is equal to x, given coyote. And so we can see that we can now directly enumerate what these optimal decision boundaries are. We can directly calculate what the error is. And as we change these individual populations, we can also see in their individual probabilities, their mu and their variance, how that changes the overall problem. In the next lecture, we'll be actually coding this up, plotting it in matplotlib so that we can use it for homework problems. And if we just want to do these calculations on the fly. Thanks so much for listening. See you next time.